Hello and welcome back. If you got a notification that I uploaded yesterday, sorry about that. I recorded this previously, but I forgot to set my OBS settings, so it only recorded like a corner of my screen. Um, Anywho, apologies that I haven't done any AOC videos yet this year. I've been quite busy. Travel, holidays, day job keeping me busy, etc. But I thought that I would start off by going over day 5 here, which I think has some neat array-based techniques and analysis that you can do on the graph that it proposes. So without further ado, let's jump into it. So day 5, as usual, there's a bunch of flavor text, but basically you get puzzle input that is split into 2 parts, and the split happens on this empty line here. The first part denotes a series of page number rules. And what this says is that the number on the left of the pipe there must come before the number on the right of the pipe for some ordering. And then we have a series of lists of page numbers. And basically we're going to be doing some stuff with ordering on these sets of page numbers. The problem says, so for part 1, we have to determine which of these sets in the second part of the input are already in the correct order. And the order is established by these ordering rules, right? And then what we do is for each one of them that are ordered, we get the middle page number, so the middle element of the list. This implies that all of them are of odd length, which they are. And we add all those numbers together, and that gives us our answer. For part 2, we have to consider the other sets that are not in the correct order. So we have to correctly order them, and then also get the middle page number and add those up, and that will give us our part 2 answer. So there's an important piece of text somewhere in here that says, when you are considering one of these sets, you only consider the ordering rules that specifically mention these numbers. So the other ones are sort of deemed not to exist. So, when we're considering this first set here, we would only look at the rules that contain like 75, 47, 61, etc. Now, if you are sort of familiar with graph theory problems, things like that, previous Advent of code problems that look like this, you may be tempted to just take these rules, construct a graph out of them, and then do something like a topological sort. So a topological sort is, when you have these type of ordering rules, you construct an ordering that obeys all of those rules. So your first element will be some node or number in this case that doesn't have anything that depends on it. And then, your second node may depend on the first node or may also have no nodes that depends on it, et cetera, et cetera. Basically, you spit out like a possible sequence that obeys all of these rules. However, in this problem, if you try this, you will find that it doesn't work, and we'll go into why. But anyway, without further ado, let's jump into this and let's just let's kind of solve the problem as given, get the answer, and then we can do some graph analysis and stuff like that. Okay, so as usual, we're going to start with inget. Sorry, it's kind of early in the morning. We'll see if I get up to speed here. So this gives us our problem input, and we want to split it on the empty line. So we can do that with like for each length, if 0 does not equal. So the empty line will have a length of 0. We can feed this as a Boolean vector to partition, and that will give us this. The shape of this is 2 elements. Great. And then for each one of the kind of inner cells here, basically we have some numbers. So in the first half, they're separated by the pipe character. In the second half, they're separated by comma. And we just pull out the digits with membership bound to quad D, which is just a kind of hard-coded string it's a constant for the digit characters 0 through 9, and we can do that to partition as well. And as long as we're in here, we can execute all of these in order to get actual numbers. And because this is still a length to array, we can do assignments to header and rest, I guess. Cool. So now we have our header, and we can get an idea of the rules if we just mix it. So for the header, I think, how do I want to do this? Well, actually, let's look at the rest first. So this, the length of the lists in rest is, they're all different. And I said earlier that the fact that it's asking for the middle elements implies that all of them are odd, which we can verify by doing mod 2 and doing an and reduce or an inner product here. So we see that they are all indeed odd. So for each one of our elements in rests, we are going to run a function. And what I'd like to do is I'd like to construct a matrix for each one. So we'll do outer product, catenate both sides on omega, and we'll just kind of look at the first element here so we can see what we're doing. So this just constructs a pair of coordinates for, well, coordinates, page numbers for each one of the numbers in our input row here. And we can get this to a Boolean matrix by doing a membership in the header there. And if we do this, so this is saying, okay, for each possible pair of the page numbers that we're considering, is there an explicit rule that states that, you know, the page number on the left has to come before the page number on the right? We get this super interesting shape on the first element. This is called an upper triangular matrix, which kind of makes sense because, you know, basically everything above the diagonal is filled in. However, if we look at the second element in this list, we get something different. So this is the difference between an input set that is sorted and one that is not. The upper triangular matrix basically means, okay, so the first element has explicit rules. So we're up here at the first row here. The first element has explicit rules that say that it has to come before every successive element. And then for the second element, it has the same thing. It has rules that state that it has to come before every successive element. So this implies a couple things. First of all, there is only one possible ordering of this. And second of all, you don't have to consider any transitive rules. So, you know, each one of these has explicit rules stating that it has to come before every successive element. And we can infer all of this just by looking at the fact that this is an upper triangular matrix here, right? Now for the unsorted one, this is a little bit more interesting. You'll recall that part 2 asks us to actually sort these, and we can do that with a grade down or grade descending. This will give us a vector, but if we want to look at the actual Boolean matrix this produces, we can just temporarily assign this to G. Oh, no, sorry. The assignment to G has to happen here, I think. And because this is a matrix, I have to index into the rows. Okay. So if we sort this Boolean matrix descending, this is a sort from left to right. Ones have to come before zeros, right? And you can kind of see that each one of the columns, that is indeed the case. All the ones come before the zeros. By doing this sort descending, essentially what we're saying is like, okay, if there's a dependency, on a certain column, it has to come before any successive anything that doesn't depend on it, right? So this is kind of like ordering the rules left to right is the way that the sorting function works, or grade. And this is actually sufficient to sort the rules. So if we take away the G assignments here, and instead we just index into omega, and of course now that I'm indexing into a vector, I can't use the semicolon. This is, let me see if I can, we'll just do this. Yeah, so this is our second element sorted according to the rules, and this is the second element as it was given to us, right? Now, we can apply this to each one of R, and that gives us a bunch of vectors, and we can assign this to like S for sorted, right? Now, the question asks for part one, actually we need something that pulls out the middle digits. So let's say for each S, we're going to take the length and divide it by 2, right? That gives us this, but you can see that we get a bunch of fractional numbers because they're all odd. So let's take the maximum, and then we can just index into the right. I need a jot here because of the way that trains work. So this is all the middle numbers. We just call this D for like digits, I guess. Okay. For part one, it asks you to add up all the middle digits for things that are already sorted. So we can just take our input rows membership into S, and that gives us a Boolean vector. So these are rows that are already sorted. This can be used to filter our digits, and we can add them all up to get 4609, which, if I can switch here, is indeed the correct answer for part one. Okay, and then for part two, it just asks, okay, what about the ones that aren't sorted? So we can just insert a not here, and that gives us 5723, which is our answer for part two. And if you want to be super duper fancy, so this input membership sorted, this gives us a Boolean vector. We could construct a Boolean matrix by doing something like this. So 1, 0 equals, and now you can kind of see that the left column has ones for everything where they're sorted already, and then the right column has ones where they are unsorted. And if we look at the shape of this, this is 2032. If we look at the shape of our middle digit array, this is also 203. So because the shapes match, now we can do something super fancy. We can just do a matrix multiplication, or a vector matrix multiplication here. So this multiplies our middle digit vector by each column. And because anything times 1 is the number itself, and anything times 0 is 0, this kind of works to just get the middle digits that we care about in each column. And then the plus side of this matrix multiply will just reduce down the columns with addition. And that will give us our part 1 and part 2 answers in one shot. Okay, cool. So that is the answers for, those are the answers for part 1 and 2. Now, let me show you why that graph analysis topological sort thing that I mentioned before doesn't work. So let's go back to our headers here. Let's enlist this, take all the unique elements, and let's sort them, because why not? So we'll sort ascending. How many elements do we have? So we have 49 unique page numbers, or you can think of these as nodes in a graph. Let's call these page numbers. Actually, in order to explain this better, I kind of mocked up just a simple kind of input that we can do here. So I haven't edited that yet. Let's scroll back up here. I want this one, and we'll do 05 no value. Oh, yes, that makes sense because blah is just. Okay, we'll just do like one. We don't really care about this part. We just want it to pass the parsing. Okay, cool. So that's our header. This is our kind of example data here. And let's do the same kind of page number thing that we were looking at. So page number is 1, 2, 3, 4, 5, right? We can construct a graph here by doing the kind of same, sort of trick that we used to generate the graph or the Boolean matrix before. So we just put all the pairs together for all of our unique page numbers, and then we can do membership into our rules. And we get a Boolean matrix that defines the whole kind of graph here. Now, a 1 here means that the kind of number that corresponds to the row has to come before the number that corresponds to the column. Maybe I can do 0 page number eliminate like this to lay the page numbers across the rows and the columns. So this 1 here means that 1 has to come before 2, 2 has to come before 3, 3 has to come before 4, and 5 has to come before 4. And that matches our rules. But these rules imply transitively that also 1 should come before 3 and 1 should come before 4. So it would be nice to get a kind of Boolean matrix that not only says, what are the nodes that this thing explicitly depends on, but what are all the transitive nodes that it depends on, right? And we can do that with something called a transitive closure. Let me get rid of this. So transitive closure is going to be, I always get these mixed up, by the way, but it's or.and. So this is an inner product, and we'll apply this to both sides. And what this does is it's taking each row of our matrix and then anding it against each column, and then doing an or reduce against the output. I don't really have the time to talk too much about like inner products and how all this works. I should really do an explainer video on inner products because I've been using them a lot more in the last year or two. They're extremely useful, and I think properly using inner products is really like the key to some of the kind of more array-based techniques and thinking and stuff like that. So maybe I'll do a dedicated explainer video on this, but for right now, all that you need to know is that this or.and is kind of one step in following the graph. So by doing this, we can now see that 1 depends on 3, which is kind of implied by our rules here. And then 2 depends on 4, which is also implied by our rules. So this is kind of one step. We can get our original back by just ORing it with the original input, right? And we can run this until it converges with power match. I've used power match a lot, but basically this kind of commute here supplies the original argument on the left of the argument of the train here, and then power match iterates the function until it converges, which means that it'll keep executing the function until the input matches the output, basically until it doesn't change anymore. So this is the transitive closure of the graph, and now you can see that indeed 1 does depend on 2, which is explicitly implied by the rules, but it also transitively depends on 3 and 4, right? So if we do this with our actual input, though, and then we have our unique page numbers for the actual input, and then if we look at the transitive closure graph, you can see that it's all 1s. We can verify this by just rabbling it all into a list and doing an and reduce. So what does this imply? This implies that not only is there a loop, so every node depends on itself, which you could tell just by looking at the diagonal of this matrix, but the loop there's one loop and it involves every node. So basically every node is reachable from every other node. Um, so this transitive closure is going to be useless in solving the problem in the general sense. And this also explains why you can't do topological sorting, because topological sorting doesn't have an actual answer in the face of a loop in the graph. The other thing that's kind of interesting, though, is if we go back up here, where was I generating the, yes, here. So let's take a look at our actual inputs. And what I'd like is, okay, once we've sorted everything, what if we put all those into, oh, it's going to take a while. We'll just look at our first, let's look at the second element because that's unsorted. So remember with the second element, this was an unsorted matrix. So it looked like this. And then once we sort it and we get the elements and we put everything back, if we then index into our rules again, we can see that it is now also an upper triangular matrix. And what this implies is that, you know, each element, so like the first element has explicit rules for all the following elements, right? So you don't need to do any, you don't need to consider any transitive rules. The input is structured such that there are explicit rules for the ordering for every possible element. And if we look at this for each one, we can kind of tell that these all look like triangular matrices. We can generate a triangular matrix, for example, with iota 5 outer product less than. So we can generate a triangular matrix of a certain size. And if we go back up here, we could say like, we could say iota length W outer product less than commute. Does this upper triangular matrix that we would expect match the actual triangular matrix that we generate? We get a bunch of ones and, okay, calm down. We get a bunch of ones and we can do an and reduce here to see that that is the case for everything. So each one, each input row when it's sorted results in these upper triangular matrices, and this implies that you never have to follow a transitive link. There are explicit rules specified for, you know, the different, the sorted pairs of elements in your input set. So this is why you can't use topological sort, and this is also why you don't have to. Not only do you not have to do that, but you also don't have to consider any transitive rules for any of the numbers in your input rows. So anyway, this is kind of a speed run. I may do more videos. Sorry again that I haven't been keeping up this year. I'm just kind of busy. And I do want to do a video at some point explaining those inner products, as I said, because I think those are really important. But anyway, if you've made it this far, I hope you enjoyed, and I will see you next time.